All right, so let's talk a bit more about hemoglobin. And remember last time we were talking about how does oxygen bind to it? Um, and we had come to the conclusion that we have a sigma type interaction and a pi type interaction. So essentially, we end up making a double bond. But there's some problems with this. So I should have said this at the beginning, but I'll say it now, and it will still remain true. This is still an area of debate. And what I mean is that there's still questions about how and what exactly happens when oxygen binds to hemoglobin. And so, in fact, the paper that I talked about in the last video there, is one of the more recent additions to kind of trying to figure this out. So what I'm going to introduce to you here are just some ideas. And, who knows, this stuff will adapt, and it has adapted when I learned about this from to begin with. So we'll try and introduce some of the new concepts for you. Okay? All right. So if you go back to the other video, let's see, do I still have this pulled up? Yes, I do. Right? If you go back to this, right, as we zoomed in, whoa, that's a bit much. Come on. This worked fine when I did my test. Okay. Right? So in the deoxyhemoglobin here, right, we talked about that, the iron center is sitting a bit outside of the plane of the heme unit itself there, right, of the porphyrin unit. So, whoops. Right? So essentially, right, we've got our iron center, right? And, right, we've got our heme, right, that's sitting in a plane here, right? And then also, don't forget the iron is bound to the histidine on the other end there, right? So what happens then is when oxygen comes in, right, as we bind oxygen to hemoglobin, what happens is the metal, okay, falls into the plane of the porphyrin. Okay, and let's bind some O2 here. Okay, and so we have to figure out what's going on with this. Okay, why does it do this? How does it do that? And there's two thoughts. The thoughts are this: one, we're going from a high spin to a low spin system. Okay, or two, we're going from an Fe2 plus to an Fe3 plus system. Say, oh my goodness, okay, what in the world does that mean? Let's try and explain this. So let's talk about the Fe2 plus to Fe3 plus system there, okay? So whenever, like I told you guys in class, right, whenever you see a protein and it's got a metal in there, one of the most important things to recognize is the oxidation state of the metal. Because that's going to have a huge impact on the properties and the structure and the function and the size and the shape, all these kind of things. So it's really, really, really important to always know what oxidation state you're working with. So if we're dealing with iron 2 plus, right, this is our 3D6, okay? And here's our 3D5, okay? So what happens as we go from Fe2 plus to Fe3 plus? Well, there's a couple things that happen, and we'll talk about the basics here, right? Well, here's a question, right? So when we change oxidation states, as we go from Fe2 plus to Fe3 plus, right? The cation, right, the iron, would get smaller. Remember, the higher the oxidation state, the smaller the ion's going to be, right? So if we transfer an electron to the oxygen, right, because that electron has to go somewhere, right? Where does the 2 plus get, right? If we're going from 2 plus to 3 plus, that electron has to go somewhere. Likely it's going to go to the oxygen, right? Where does that electron go, right? And the consequence of this is, right, the cation's going to get smaller. So the thought is that iron 2 plus is too big of an ion to sit in, right, to sit inside the porphyrin ring. right? But if it goes to 3 plus, then maybe it gets smaller and it can fit inside the porphyrin itself. So, okay, that kind of makes sense. Why? Why would it want to do this to begin with, right? Why would it want to do this to begin with? Why would it want to change size and fit into the porphyrin ring itself? Okay, well, we're asked a pretty darn complex question, and we can always fall back on the idea of sterics and electronics, right? That's kind of a good place to start. Sterically, right, there's not much of an argument to be made here, right? So let's talk about electronics. Well, here's the idea, right? Let's think about it like this. So here's just our, kind of a, let's say, a zoomed in side-on view of the porphyrin itself. So remember the way, right, the way that that the porphyrin is going to bind to the metal is that the orbitals have to overlap, right? And if we've got the iron that's sitting outside of the plane, right? If the iron's sitting outside of the plane of the porphyrin, right, the orbital overlap's not going to be as good. As opposed to, okay, if we move the iron into the plane of the porphyrin, right, then we can have a nice overlap of all the different orbitals, aka we can start to make a stronger bond, which is what these things want to do, right? We want to make bonds between our ligands and our metals. Those are stabilizing effects, right? And then we can talk about, bonding theory and all that kind of stuff, right? So the iron sitting outside of the plane of the porphyrin actually weakens the bonds a bit, and as it falls into the plane, right, we can strengthen those bonds, and that's a good thing. Okay, so there's an electronic motivation for the iron to fall into the plane of the porphyrin, right? It strengthens those bonds. Now, obviously, I'm just representing generic orbitals here, right? We have our x squared minus y squared, our z squared, all these different things that are kind of at play here, right? So don't think that this is some kind of comprehensive list. The only point I want you guys to think is that as we move into the plane of the porphyrin, we start to increase the bonding with the porphyrin itself, between the iron and the ligand. Okay. So, okay, that's why this wants to happen. Now we have to answer the how, right? And so one theory is that as we go from Fe2 plus to Fe3 plus, right, our cation is going to shrink in diameter, right? And so then it can fit into the plane of the porphyrin. So, okay, that seems logical. There's some problems with this. Iron 3 plus has some solubility problems. It has reactivity problems, right? This may or may not be that good of a theory. Iron 3 plus in biological systems, it certainly can exist, right? And we'll talk about some examples of those later, right? But within hemoglobin itself, it tends to cause some problems. In fact, there is a problem where hemoglobin can get stuck in the +3 oxidation state, and then an enzyme has to come through and reduce hemoglobin back to the Fe2 plus to continue to do its job. And the name's escaping me off the top of my head. I know it's in one of my notes somewhere. In fact, you know what? Let me pause here real quick. Since I'm a dum-dum and I forgot to write this down. So let me go look this up real quick. I'll be right back. All right, I found it. So, took a little bit longer than expected, but let's see here. METH, methemoglobin reductase. Okay. So there are some times where hemoglobin gets stuck in the +3 oxidation state, and that's called methemoglobin, right? And so then we need methemoglobin reductase to kind of bring it back to the 2 plus so it can bind oxygen. Okay. So the point being that we have to be careful, using this 3 plus oxidation state idea in hemoglobin, because that can cause some problems down the road. Okay. All right, but we're not going to talk about this stuff right here. But if you want to pop that into Google, right, it'll give you some cool information about how that works. Okay. Anyway, so one thought is we have a 2 plus 3 plus change in oxidation state, right, which changes the size of the cation, and then it's going to fall in. Okay. Let's talk about the high spin and low spin state here. So let us look at the molecular orbital diagram for a generic high spin versus low spin octahedral complex. Okay. So we're looking at Fe2 plus, right? Here we have our high spin, and here we'll have our low spin, okay? So if you guys want to take a second here, and if you guys want to plop in and fill in the electrons and the orbitals and all that, that'd be kind of good practice for you guys. X squared minus y squared, z squared, and xy, xz, yz, xy, xz, yz. Okay? So we have 3d6. We'll do this in green. All right. High spin, 1, 2, 3, 4, 5, 6. And versus low spin, 1, 2, 3, 4, 5, 6. Okay. Whoops, and I should give these labels. This is our EG, and this is our T2G. I don't know why I capitalized that G. Not that it really matters. Oops, and I ran out of space, or T2G. Okay, cool. So hopefully you guys came up with something like this. Okay, so that should explain, right, why the change from high spin to low spin should be able to make the iron fall into the porphyrin center. Good? What? You mean it doesn't make sense? Aha, you guys forgot something. You guys forgot something important. Okay, remember, the EG set is anti-bonding, okay? So here's a thought. What changes as I go from high spin to low spin? Well, as I change from high spin to low spin, I take electrons out of my anti-bonding set. So remember, if I populate an anti-bonding set of orbitals, I'm going to increase the bond length. If I take electrons out of that anti-bonding set, right, I'm going to make stronger bonds. I'm going to shrink the bonds, right, and that effectively lets me sit the iron as a 2+ oxidation state into the porphyrin itself. So we're kind of playing off the same idea here. We're kind of changing the size, so to speak, but we're looking at how, right, how the change of populating an anti-bonding orbital versus not populating that orbital changes our metal center, okay? Anytime you put electrons in an anti-bonding orbital set, we increase that bond length, right? So if we take things out of it by changing from high spin to low spin, right, then we effectively shorten those bonds so the metal can sit inside the porphyrin ring itself. Okay? Don't forget that that EG set there is anti-bonding. Okay, so then we get to finally the crux of the matter. Which one of these is correct? Well, here's the thing, okay? Here's the thing. And what I would recommend is you guys pull up the Wikipedia for hemoglobin, and there's a good chunk in there that kind of goes into more detail about this. The answer is it's probably a combination of these two, wherein the high spin, low spin transition is the dominant feature, though. We didn't talk about it in this class because we don't have the time to kind of go into the detail, but there's some spin issues that occur when oxygen binds to hemoglobin. Okay? And so we didn't talk about that, and you know, in the article on Wikipedia it talks about symmetry and spin states and all this kind of stuff. And those are important, right? And I'm not dismissing those at all by any means. But I'm just saying, like, for the context of the course that we're trying to talk about here, we just didn't go into that. But the answer is, you know, predominantly it's going to be this high spin, low spin transition, but there is some evidence for the iron 3+ to exist to some small amount. So really, if you want to think about this, right, if you remember back to your idea of organic chemistry, there's the idea of resonance, right, where we have all these different structures existing simultaneously to some percentage. Maybe that's the idea to kind of bring into here, right? Both of these ideas together to whatever percent contribution contribute to the fact that when oxygen binds to iron, it will drop into the porphyrin itself, which causes some changes in the structure. And then, right, you know, we can talk about allosterics and all that stuff there, okay? So the answer is both, but predominantly this is going to be the most important transitions to happen, okay? Now, we're not going to talk about allosterics for this course, just because we don't really need to, right? And I think you guys probably talk about that in biochemistry anyway. But, right, allosterics is just talking about, you know, what happens and the cooperative effects and all this kind of stuff within hemoglobin there and other enzymes. But anyway, that's a little bit outside of what I want to talk to you guys about. What I want to talk to you guys about is what happens at the metal and what are some of the properties and things that we see at the metal center itself, right? So 2 things to always think about, okay? 2 things I want you guys to start to think about when you see a metal in an enzyme, right? As we start to bind something, is there going to be a transfer of electrons, aka do we see electrons getting transferred from one to the other? And what impact does that have on the metal? Or do we see a change in the spin state? Or do we see both? Okay? So always important to pay attention to what the oxidation state is of the metal that you're looking at, and always important to take a look at the spin state of the metal that you're looking at also. And it just so happens that hemoglobin is kind of a good example where both of these occur, and both of them can be used to theorize as to what happens when oxygen binds to the metal center of hemoglobin there. Okay? All right, so take a look at the notes that I post online for you guys too, right? And I will see you guys in the next video, and we'll just continue chugging through this.